When you flip a light switch, the light comes on pretty much instantly, right? But here's the crazy part. The tiny little particles that are carrying all that energy, they're actually moving slower than a snail. So, how is that even possible? Well, that paradox is really at the heart of what electric current is all about. And today, we're going to unravel that mystery. We're going to break down the physics of this invisible flow that powers, well, our entire world, from your phone right down to a single chaotic electron.
So here's the game plan. We'll kick things off by picturing current as a river of charge. Then we're going to zoom way in and uncover the truly shocking truth about its speed, which we're calling a snail's pace. After that, we'll take a look at the universal obstacle that gets in the way of this flow. Yep, we're talking about resistance. And finally, we'll see what happens when that flow fights back in Energy Unleashed.
All right, let's start with part one and that idea of a river. It's a really great way to think about electric current, but it does make you wonder, what exactly is flowing between the banks of that river? Seems like a pretty basic question, doesn't it? But the secret is all in the details. See, it's not just about charges moving, because in any piece of metal, the electrons are already zipping around like crazy in totally random directions at insane speeds. For a current to actually exist, you need a net flow, a collective movement in one direction. So, to put it a little more formally, electric current, which we symbolize with a lowercase I, is all about the rate of flow. Now that formula, I equals dq over dt, might look a bit intense, but all it's saying is this. You just measure a certain amount of charge, dq, that flows past a point over a certain slice of time, dt. The unit we use for this is the ampere, or just amp for short. And 1 amp, well, that just means 1 coulomb of charge is cruising past you every single second. Now, in a simple, unbroken wire, the current has to be the same everywhere. This whole idea comes down to one of the most fundamental rules in physics, the conservation of charge. You can't just create or destroy charge out of thin air. So for every electron that you push into one end of a wire, another one has to pop out the other end. It's kind of like a garden hose that's already full of water. The very instant you force a new drop in, a drop has to come out the other side. And that exact same rule applies when the path splits, like at a fork in the road. If a main current, let's call it I0, hits a junction, it might split into two smaller currents, say I1 and I2. But because charge is conserved, the total amount flowing in has to equal the total amount flowing out. So I0 has to be equal to I1 plus I2. It's just simple accounting, really. There's nowhere else for that charge to go. Okay, so we've got this river of charge, right? And you'd probably think the electrons themselves are just speeding down that wire. Well, this is where things get a little weird. Let's zoom in to the microscopic level, and you might want to prepare for a surprise. So, to really get a handle on speed, we first have to talk about something called current density, or J. It's really just a measure of how much current is packed into a certain area. When a wire gets narrower, that same amount of current gets squeezed into a smaller space. The flow lines, as you can see, they get closer together. That means the current density is higher. It's exactly like water flowing from a wide, lazy river into a narrow, raging canyon. The flow gets way faster and a lot more intense. And this idea brings us to something called drift speed. See, when you apply a voltage, you create an electric field, and that field gives the electrons a little push. But it's not like they have a clear runway ahead of them. They are constantly crashing into the atoms of the wire, bouncing around all over the place. Drift speed is the average speed they manage to achieve in the direction of the current, despite all that chaos. It's their net forward progress. So what is this actual drift speed? Well, get ready for this. Look at that number. It's almost unbelievable. It's about half of 1/1,000,000th of a meter per second. To put that into perspective, an electron in a typical wire moves less than 2 millimeters in an hour. That is, and I mean this literally, slower than a snail. The very particles powering your high-speed internet are moving at a truly glacial pace. Which, of course, leads to the most obvious and perfectly reasonable question. If the electrons are moving so ridiculously slow, why in the world does the light bulb on the other side of the room turn on the very instant you flip the switch? How can that be? And here's the solution to the whole puzzle. It turns out there are two different speeds at play here. First, you have the drift speed. That's our snail, the slow, physical movement of each individual electron. But then there's the signal speed. The moment you flip that switch, an electric field, basically a get moving command, zips through the entire wire at nearly the speed of light. This signal doesn't carry electrons from the switch to the bulb. It just tells the electrons that are already sitting at the bulb to start moving. Think of it this way. The command is fast, not the soldiers. So why is that drift speed so slow in the first place? Well, it's because those electrons aren't just cruising down an open highway. Their journey is a constant battle, a constant struggle against a universal obstacle. And that obstacle is called resistance. Resistance, which we write as R, is a measure of how much a specific object, like a certain length of wire, fights against the flow of current. We define it with this formula here. Resistance is the voltage, V, you put across the object, divided by the current, I, that manages to get through. Its unit is the ohm, and we use that Greek letter omega to represent it. So resistance describes an object. But what about the material it's made of? For that, we use something called resistivity, symbolized by the Greek letter rho. You can think of this as a material's fundamental stubbornness against letting charge flow. Copper, for example, has a super low resistivity. It's very easygoing. Glass, on the other hand, has an incredibly high resistivity. It's a property of the substance itself, no matter its shape or size. Okay, so let's put these side by side because this is a really crucial point. Resistance, on the left, is a property of a component. It depends on the material, sure, but also on its length and its thickness. A long, skinny copper wire has way more resistance than a short, fat one. But resistivity over on the right is a property of the substance. All copper, assuming it's at the same temperature, has the exact same resistivity, whether it's a wire or a block or a coin. Now, this brings us to Ohm's law, and here's something that trips a lot of people up. Ohm's law isn't just the formula V equals IR. That's actually just the definition of resistance. Ohm's law is the specific claim that for some materials, that resistance value stays constant. As you can see in the table, a simple resistor, well, it obeys Ohm's law. But lots of other components, like a diode, absolutely do not. Their resistance changes all over the place depending on the voltage you apply to them. Okay, so we've got this constant struggle going on. A current of electrons being pushed through a material that is actively fighting them. And this battle, well, it isn't free. It costs energy. That transfer of energy is what our final section is all about, electric power. Electric power, P, is simply the rate at which a circuit does work or transfers energy. You can just think of it as the circuit's oomph. And the basic formula for it is just beautiful and simple. Power is the current multiplied by the voltage. We measure it in watts, and 1 watt just means 1 joule of energy is being used every single second. Now, when this energy transfer happens inside a resistor, almost all of it gets converted into heat. We call this resistive dissipation. It's the reason your toaster gets hot. By combining our main power formula with Ohm's law, we get 2 really useful shortcuts. If you happen to know the current and the resistance, power is just I squared R. If you know the voltage and the resistance, power is V squared over R. Both formulas tell you the exact same thing, how fast that component is generating heat. And this brings us right to the purpose of these little guys, which are called resistors. Their whole job is to be put into a circuit on purpose, to intentionally add resistance, to control the current, and to safely turn electrical energy into heat. The very formulas we just talked about are what engineers use every single day to make sure our electronics work the way they're supposed to without, melting. So, resistance. It seems like this fundamental hurdle, right? An unavoidable tax on energy that we always have to pay in the form of waste heat. But what if it wasn't? What if we could actually build a wire with 0 resistance, creating a perfect electrical superhighway? Well, that is the incredible promise of superconductors, but that, my friends, is a story for another time.